Welcome back to the deep dive. For this session, we are stripping away all the layers of modern operating systems.
All the GUIs, all the polished apps.
Yeah, exactly. We're going straight to the digital bedrock. We're talking about the sources of true, lasting computational power, and we're drawing it directly from the legendary UNX Power Tools, 3rd edition.
You know, that source material, it's so much more than a book. It's almost a philosophical treatise on efficiency. And our mission today is pretty straightforward.
Right.
This is not a history lesson. We are here to extract the highest leverage knowledge. We're talking concepts, shortcuts, and those definitive, aha moments. The kind of stuff that fundamentally transforms how you interact with any modern operating system, whether it's Linux, Mac OS, or some dedicated server somewhere.
Exactly. We're just bypassing all the pretty window dressing and cutting straight to the kernel of productivity. The book makes it so clear.
It does.
The core of efficiency is not in the graphical user interface. It's in mastering the foundational concepts of the shell and the file system. I mean, if you can learn how to automate a task in a few keystrokes,
A task that would take hundreds of clicks.
1,000 clicks, then you've become a power user.
Yeah.
And that really is the knowledge we're aiming to deliver to you.
The whole Unix philosophy is built on elegance, on simplicity. It's all about small, specialized tools that just fit together beautifully. So I think we have to start by understanding the landscape where all these tools even operate.
Okay, so let's start literally from the root. We're talking about the hierarchical file system, the HFS. This isn't just a place to store files, right?
Not at all.
It's the conceptual map that defines how everything is organized and, crucially, how everything is located.
That's right. The whole structure, it begins at the root directory, which is just that single slash ando-char hanchi. And, this design choice, which was adopted so early in the development of Unix, it was revolutionary.
Because it imposed order.
It imposed order on incredible complexity. Think of the HFS not just as a filing cabinet, but more like a massive digital tree. Every file is a leaf or a branch, and every directory, well, it's just a special kind of file that points to other files.
It avoids that chaos of just having everything dumped in one massive flat heap.
Which would be totally impossible to navigate, yeah.
And the beauty of that structure, it really dictates how we navigate. I mean, we rely on the difference between absolute and relative path names.
Precisely. An absolute path name, that's your guaranteed route. It always starts from the root, from bottom. So, for example, a solo go bin my script. It doesn't matter where you are in the file system.
It will always work.
That path will always find the target file. It's reliable, but
it's often really long to type.
Yeah. Which is why the alternative, the relative path name, saves so much time.
Okay, so a relative path name relies entirely on your current working directory.
Completely. If you're already in uslocalbin and you want to open my script, you just type my script. But if you want to, say, jump up one level, you use cora ... to refer to the parent of your current directory.
And this single dot, it's just the current directory itself.
Right. These are such critical shortcuts. And if you ever lose track of where you are in this massive tree, the command pwd print working directory will instantly reorient you.
I think so many users just take those abbreviations for granted. I mean, we use C to D constantly, but speaking of efficiency, the sources bring up a fantastic pro tip for navigation that is, I think, often overlooked.
Oh, you're talking about CD path.
Yes.
CD path is a real deep cut, but it offers huge efficiency returns. So many of us, we frequently jump between the same few directories that might be buried 4 or 5 levels deep.
All the time.
So if you configure the CD path environment variable usually in your .profile or a .bash occur, you can specify a list of directories the shell should search before it tries to resolve a path relative to your current location.
So instead of having to type out like CD home is Regex client Xerica layer every single time,
right,
you could potentially just type CD apple layer.
Exactly. If you just include home user projects client XRC in your CD path, when you run CD apple layer, the shell quickly checks that predefined path, it finds the directory, and it changes to it.
You're saving dozens of characters per command.
Which adds up. It really maximizes efficiency over a workday. It's a mechanism specifically designed to streamline that conversational nature of working on the command line.
Okay, so once we've mastered navigation, we have to understand the middleman, the shell as the interpreter and gatekeeper. The shell isn't the operating system kernel itself, it's the layer you're talking to.
That is the crucial conceptual barrier. The shell, whether it's bash or zsh or an older born shell, it's the command interpreter. Its entire job is to read the line you type break it down, handle variables, manage I/O redirection,
Everything.
and then ultimately execute the program you asked for. It mediates everything you do, and understanding how it runs programs is, well, it's the key to optimization.
And this brings us right to a fundamental efficiency difference.
Right.
Internal versus external commands.
This is where performance lives or dies, really. An internal command, something like cd or alias or export, is built directly into the shell's own code.
So it's part of the shell program.
Right. When you execute cd, the shell just changes one of its internal environment variables. It happens instantly because no new program has to be loaded from disk.
But external commands, like else or grep, they're totally separate programs that live as files on the disk. So what's the process the shell undertakes to run one of those?
It's a two-step and kind of expensive process that involves system calls. So when you type else, the shell must first use the fork system call.
Yeah.
Fork essentially clones the entire running shell process. It creates a new exact copy of the parent process, its memory space, its open file descriptors, all the environment variables.
Wow, the whole thing.
The whole thing. That copy, the child process, then immediately executes the exec system call. And exec replaces the cloned memory space of that child process with the code of the new program, in this case L. The original shell then just waits for that child process to complete.
So fork and exec, together, they're responsible for running every single external utility. If fork copies the entire memory space, even for a moment, that explains why external commands have this measurable overhead compared to the internal built-ins.
Precisely. It's a really clever, robust mechanism for creating processes, but it's resource-intensive. Using a shell built-in avoids that entire cycle, which is why for simple tasks, shell functions and aliases that use built-ins are always going to be faster.
So how does the shell know whether to look for a built-in or to start hunting for an external executable file?
It checks its list of built-ins first, always. If it doesn't find a match there, then it relies on the path variable.
Right, the path.
The path is just an environment variable that contains a colon-separated list of directories like bin.usrbin.usrlocalbin. The shell checks those directories sequentially, one by one.
And it stops at the first one it finds with the right name.
It stops at the very first executable file it finds with a matching name. Yeah.
So if I install a custom utility in, say, opt_my_toolbin, I have to make sure I update my path to include that directory. And I guess ideally I put it early in the list so this shell finds my version before system default.
That's exactly right. It's a prioritized search path. This variable dictates the reliability of every script you write, especially when you're writing shell scripts. It's also why, as a rule of thumb, system administrators will often use absolute paths yours and find instead of just find in their critical scripts.
To be absolutely sure.
To ensure they are always executing the exact version of the program they intend, regardless of what's happened to the user's path.
Fascinating. Okay, let's get into the abstract definition of a file, which leads us to this distinction between a file's name and its true identity. File identity, inodes, and links.
This is such a critical conceptual core of Unix file systems. Every single file has a unique identifier, and it's known as the inode number.
The inode.
The inode contains all the file's metadata: its size, permissions, owner, timestamps, and most importantly, the pointers to the actual data blocks on the physical disk, the file name that you see. It's nothing more than a convenient human-readable label that points to that inode.
So if I create a file, file A, it gets an inode number. What happens when I create a hard link to it?
When you create a hard link, so ln file A, file B, you are essentially creating a second file name that points to the exact same inode. The inode's internal link counter then increments to 2.
So they're not copies?
Not at all. They are truly identical. You can't even tell which one was the original name. If you modify file A, you're modifying file B because they share the same data blocks on the disk.
And the practical consequence of this?
The critical consequence is that the file data is not removed from the disk until every hard link pointing to that inode is deleted, and that link count finally hits 0. Oh, and hard links also can't cross file system boundaries.
Okay, so contrast that deep equality with symbolic links or soft links.
A symbolic link, or a symlink, so NNS file A, file C, is a very different beast. It is a separate, special type of file that contains only a path pointer, a text string, to the target file or directory.
So it has its own inode.
Exactly. The symlink has its own unique inode number and its own metadata. When you try to access the symlink, the operating system kernel intercepts that request and just redirects you to the target path that's contained within the symlink file.
And the sources really emphasize that while symlinks are flexible, You can link directories, span file systems. They do introduce this problem of staleness.
Oh, yes. Stale and solid links. Because a symlink is just a pointer. If you move or rename or delete the target file, the link still exists, but it points to a non-existent location.
And you get that no such file or directory error.
You get that frustrating no such file or directory error, even though Siles is telling you the link itself is still there. This is such a common point of failure in large, complex systems.
Hard links don't have this problem.
Hard links avoid this entirely because the file name is the file. If the name exists, the file exists, period.
The power user trick here, the one that's often forgotten, is using relative path names when you create symlinks, especially when you're dealing with like software deployments or configs that might be moved around as a group.
That is the key to robust deployment. If you link usrel open project version 1 to usrel open project current using an absolute path, and then later you move that entire usrel open project directory to opt project, your link is broken.
Right.
But if you use a relative path when creating the symlink, it remains valid as long as the relative distance between the link and its target is maintained. It allows for seamless relocation of entire directory structures.
Okay, so we've established the foundation. Now let's get into the practical application of this knowledge. Actively managing thousands of files. We can start with listing and sorting files with intent options.
The default alphabetical sort of Ls is, it's useful only in simple directories. A power user needs to leverage file metadata to quickly find what they need, and that requires understanding the 3 Unix file times.
Break those down for us. What are they and why do they actually matter?
Okay, so first, the modification time. This is the time the contents of the file were last changed. It's the most common time used for version control, that kind of thing.
Makes sense.
Second is the access time, A time, which is the time the file was last read or executed. This one's a bit controversial because just accessing a file updates its metadata, which can cause performance hits.
Right, though modern systems have workarounds for that.
They do, yeah, deferred updating and things. And third, there's the inode change time, kick time. This is the time any metadata about the file changed, permissions, ownership, number of hard links, anything like that.
So if you change a file's content, deck time also updates, but you can change deck time without changing the modification time.
Exactly, like just changing its permissions.
So how do we actually use this with else?
Well, the most immediate benefit comes from sorting by time. The flag else_gati sorts by the modification time, and it places the newest file you edited right at the top. So if you just finished working on 3 scripts and you need to zip them up, else_gati gives you exactly those 3 files first.
And for system hygiene, we'd use the access time.
Crucially, of else-2 sorts by the access time, and it shows the files that were used longest to go first. So if you're cleaning up a server, trying to identify archives or executables that haven't been touched in a year, this command is invaluable.
So modification time for what you just worked on.
And access time to find what you should probably delete. That distinction is a core power user move.
We also have to shine a light on the invisible parts of the file system, hidden files.
Unix has this really simple convention. Any file or directory that starts with a period, a dot, is considered hidden.
And it's just a convention, right? Not a special file attribute.
Purely convention. And these are almost universally configuration files like .bashrc, .vmrc, or your cheshconfig directory. Standard ls just ignores them.
So you have to use else.
You must use else. That shows you every entry, including the special and directory references. They're only hidden to keep your working directory uncluttered.
Okay, so beyond sorting, immediate visual identification is a huge time saver. That's where visual cues come in.
Yes, the classic ls-f. It adds these little type indicators to file names. A / immediately tells you it's a directory.
An asterisk for an executable.
An @ means it's a symbolic link. A pipe symbol denotes a FIFO, a named pipe. It allows for lightning-fast scanning of a directory listing. It eliminates the need to run file on everything.
And building right on top of those visual cues, we have utilizing color roles for rapid identification.
Oh yeah, colorized Ls, especially the GNU version that's widely used in modern Linux, it takes this visual identification to a whole new level. Directories are blue, executables are green, symlinks are sky blue, and so on.
It just minimizes your mental load.
It does. It provides instant peripheral vision feedback about what kind of file you're looking at.
I remember when I first tried to figure out how to configure the colors, it was so opaque. It's all driven by that lscholars environment variable, which, it just looks like gibberish.
It truly does. If you print lscholars, you see this long string of semicolon-separated definitions like die01 .34.ex0132. It's just mapping file types, like die for directory, X for executable, to these ANSI escape codes for coloring.
Like 34 for blue and 01 for bold.
Right. Trying to set that manually is just pure misery.
So how do you actually configure this effectively?
You rely on the utility dir colors. You run dir colors first, and it outputs a shell command and assignment to the else colors variable based on a config file. Then you use the evil command to execute the output of dir colors in your current shell.
It's a common pattern, right? One program generates settings, and evil executes that generated code.
Exactly. It's an elegant, if a little complex, piece of shell bootstrapping. It ensures the variables are set correctly for your shell session.
Okay, now that we can list files, let's talk about finding them, which brings us to the power of find. And I think the biggest conceptual error people make is thinking of find as just a passive database search.
It's not. That's the core insight from the source material. Find is an expression evaluator. It walks the directory tree you specify, and for every single file it encounters, it evaluates a series of conditions you provide, like new name, new type, user.
And it only acts on a file if the whole expression evaluates to true.
You are defining logic, not just searching some pre-indexed database.
And when using the no-name expression, we absolutely must talk about wildcard safety. This is a landmine for new users.
It is the most common and potentially destructive beginner mistake. If you want to find all your C source files recursively, you might type find.name.c.
Without quotes.
Without quoting the wildcard. And if you do that, the shell sees .c first. If there are any C files in your current directory, the shell expands that wildcard before passing the argument to find.
So find never even sees the pattern.
It just receives a list of file names.
Oh.
And if you're searching in subdirectories, it's just not going to work right. It leads to really confusing, incomplete results.
So the rule is absolute. When you use wildcards within find operators like bcname, they must be quoted.
Usually with single quotes, yeah. Find.name.cs. You have to prevent the shell from expanding them prematurely. The single quotes ensure that the literal string.c gets passed to the find program, which then handles the matching itself.
And failure to quote is often a silent failure.
Which is the worst kind of bug.
Another functional limitation of find is time resolution. The standard operators, they only work with whole days. How do we get around that?
This is a classic power user trick. Precision time searches. Standard operators like a char time or mtime, they are limited to 24-hour increments. So if you need to find all files modified after a specific minute, say, after a system update that happened yesterday at 4:30 p.m., the standard operators are useless.
So the solution involves creating a reference point.
We use the touch command. Touch can set the timestamp of a file to any specific time you want. So first, you run touch st with a custom time format to create a checkpoint file, checkpoint.ts.
With the exact timestamp you want, down to the minute.
Right. Then you use the day or newer operator, find path-newer shellpoint.ts. This tells find to locate any file whose modification time is newer than the modification time of that checkpoint file.
And that gets you minute-by-minute resolution.
Which is a necessity for auditing or recovery.
So once we've located the target files, we need to take action. Just listing them is only half the battle.
Yeah.
We need to explore executing commands on found files.
The standard methods are pipes and zargs, or the internal exec operator. Now, if you pipe the results of find to a command, say find sling print command, you have a fundamental problem.
The argument list too long error.
Exactly. Most shells have a pretty small limit on how many arguments you can pass to a single command. If your find returns 50,000 files, the command will just fail.
That's where zargs comes in as the essential middleman.
Yes. Zargs reads that list of file names from the standard input, the pipe, and it intelligently bundles them into smaller groups, running your command multiple times. It makes sure the argument list never exceeds the shell's limit.
So for bulk operations, you absolutely need it.
For running gzip on thousands of files, you absolutely need zargs. And we often use dragger print and neselair to handle file names that might contain spaces or other tricky characters.
And what about using find's own internal command execution?
That's the exec operator, find nasmname.o.exec when age ab. The curly braces are replaced by the file name, and the escaped semicolon terminates the command.
The advantage there is that it runs the command one file at a time.
Which is sometimes necessary if the command you're running needs specialized input or you just need a simple one-off operation.
And for safety, especially with destructive commands like arm or chown, the sources suggest the safer cousin of execs.
Ah, yes, the OK operator. It works exactly like exec, but it prompts you for a Y or N before executing the command on each and every file.
It gives you a chance to approve or reject.
It provides an interactive safety net against accidental mass deletion. It's a real lifesaver.
We've covered the digital workspace. Now let's focus on immediate gains right at the keyboard interface. And we have to start with the most critical and probably least forgiving element of the shell.
Oh, you mean the critical role of shell quoting?
That's the one.
Quoting is the language of control in the command line. It's what separates a literal string from a command interpretation. And the core principle is, well, it's immutable.
Which is?
Quoting disables the special meaning of characters. Without proper quoting, the shell will try to interpret $signs, asterisks, pipes, semicolons, and it will often lead to chaos.
Okay, let's look at the strongest quote. Single quotes.
Single quotes are the brute force option. They suppress everything. If you put a string inside single quotes, the shell treats it as a purely literal string. No variable substitution, no command substitution, no wildcard expansion, nothing.
And this is necessary when you're passing complex, regular expressions to things like grep or sed.
Absolutely. Because characters like all need to be treated as literal parts of the pattern, not shell special characters. The only limitation, of course, is that you can't nest single quotes. There's no way to escape a single quote inside of single quotes.
Which brings us to the more nuanced double quotes.
Right, so double quotes are strategically weaker. They still suppress most of the dangerous characters, like wildcards and spaces, but they intentionally allow three things to keep their special meaning.
Okay, what are they?
The $sign for variable substitution, the back quote for command substitution, or the newer one, and the backslash for escaping characters.
So if you need to include a variable's content, and that content might have spaces, you have to use double quotes.
You must echo. The file is named file-a-name. Without the quotes, it would fall apart.
And this leads us back to this source's terrifying anecdote about the necessity of testing wildcards before you pass them to a destructive command.
It's a lesson you only want to learn once. The anecdote of the user typing ARM because they thought they were targeting only files starting with 4 question marks. It's just a perfect illustration of the danger.
The shell just extended it.
The shell, did it say, expanded it to every file in the directory that matched any combination of 4 or more characters and, well, deleted them all. The shell is incredibly literal.
So the only way to ensure safety is to use echo first.
Always. If you plan to run arm-rf path your input, run echo arm-m arm-rf path your input first. Observe precisely what the shell expands before you actually execute it. That is the fundamental rule of command line survival.
Okay, moving from safety to speed, let's talk about leveraging what we've already typed using history substitution shortcuts.
The character, the bang, is your gateway to history. The command history system stores everything you type, and substitution lets you reuse and modify pieces of those past commands without retyping the whole line.
The quickest fix for a typo is the caret replacement.
Oh yeah, the caret replacement, old new. It's brilliant for immediate small changes. If you just typed a command and realized you misspelled one word, typing wrong right executes the previous command with the first occurrence of wrong replaced by right.
Simple, immediate, and super common.
Extremely common among power users.
But the real time-saving power lies in advanced argument reuse.
Absolutely. You can reference specific arguments from past commands. The symbol refers to the last argument of the immediately preceding command.
Right, so if you just ran tar-czf project.tar.gz date-long path to a project.
You can immediately navigate there with cd-amados. It's incredible. Furthermore, you can reference the last argument of a specific previous command by searching for the command name.
Like?
Right. If the last command starting with M was mvreporttv1.txt archive, then M refers to archive. It saves an incredible amount of typing for chained commands.
And for large-scale typos, when you've made the same mistake multiple times in one command line, we need global substitution.
Yeah. If you executed a complex command with a variable or directory name, say old proj, that appeared 3 times, and you realize it should have been new proj, you need global substitution.
So you type dsold proj new proj.
Right. Dsol refers to the entire previous command. The G modifier, which is positioned before the S for substitute, is a bit non-intuitive, but it's essential.
Because without it, it only substitutes the first one.
Only the very first occurrence, leaving the rest of your command broken. You have to remember that G modifier.
Let's pivot to customization. When should we use an alias versus a function? This is the debate of aliases versus functions. Choosing the right tool.
Aliases are simple. They're just text substitutions defined right in the shell, used primarily for giving commands default options or shorter names. Alias, alias, color auto, df is the classic example.
Easy to write, very fast.
But they are limited. They're mostly just text replacement, and they run in the current shell session.
But what is the fundamental limitation of an alias, or even an external shell script, when you compare it to a function?
It's the process space. The crucial rule is that an external shell script runs in a subshell, a separate process created via fork and exec.
So when that subshell terminates,
Any changes it made to the environment, like changing the working directory or setting a new variable, are lost when control returns to the parent shell.
which is why you can't write a script that successfully runs CD.
You can't write an external script or an alias that executes CD and actually changes your current working directory. It's impossible.
And that's why functions are the true power move.
A function is a block of shell code that runs in the current shell process. Because it runs locally, it has permission to modify the shell's environment. A function can execute CD, it can set environment variables, it can define aliases that will persist. If you want to create a reusable command that changes directory and then lists the contents, it must be a function.
The sources provide that excellent multi-line example using the mx function for DNS lookup.
Oh, that's a great one. That function demonstrates genuine shell programming embedded directly into your environment. It takes command line arguments, host names, it uses a for loop to iterate through them, and for each host, it runs dig to do a DNS query.
And it pipes the messy output of dig into a filtering pipeline.
Right, using grep and sed to extract only the necessary answer section details, specifically the mail exchanger records. This whole complex workflow looping, piping, filtering becomes instantly available as a single command, mxgoogle.com.
All because it lives as a function inside your shell.
Exactly.
Okay, finally, we hit the technical peak of shell control, the power of evil and command construction. This tool is so necessary for dynamic scripting, but it's often misunderstood.
Evil is complex because it involves manipulating the shell's interpretation process itself. So normally, the shell performs a single pass of expansion. First variables, then command substitution, then it resolves wildcards, and finally it handles I/O redirection.
But what if I build a command line dynamically, where one variable contains another variable, or where a variable literally contains a redirection symbol?
That's where the normal one-pass expansion just fails. Let's say you set readyars output.txt, and then you try to run as reader.
The shell performs variable substitution.
Right, so the line looks like L's output.txt, but by the time the shell gets to the I/O redirection phase, it's too late. The shell sees as a literal string argument to L's, and L's tries to find a file named L's. The command fails.
So evil forces the shell to reevaluate the line.
Exactly. When you run evil's radar, the first pass substitutes readyar to generate the string L's output.txt. Then evil forces the shell to process that resulting string a second time, and in that second pass, the shell correctly recognizes the shell as an I/O redirector, and the command executes successfully.
So evil is crucial whenever you're dynamically constructing shell commands.
Absolutely. Especially when you're using variables that contain special shell syntax. Without evil, those complex strings, as the source warns, they just blow up in all sorts of bizarre ways.
Okay, moving on to the utilities that really define Unix's power for batch processing. These tools are the engine of automation, designed to handle massive amounts of data non-interactively. We have to start with send, the stream editor for targeted changes.
Send is a stream editor. It reads input line by line from a file or from a pipeline. It applies a script of commands to that line, and then it writes the result to standard output.
And it's fast because it doesn't load the whole file into memory.
Exceptionally fast and efficient for exactly that reason.
Its primary function is pattern-based substitution.
The substitution command, pattern replacement flags, that's the workhorse of sed. And you can target the substitution using line numbers or regular expressions as addresses. So something like setstent 10,020 sold_newfile.txt.
We'll substitute all occurrences of old with new, but only between lines 10 and 20.
Globally, with the G flag, yes.
So what is sed's main conceptual limitation, and how do power users try to work around it?
Its limitation is that it's primarily line-oriented. It processes one line, then it moves on. So if you need to search for a pattern that spans a new line character, say, finding end of sentence, followed by start of new paragraph, sed struggles with that.
Because the pattern is split between two different records.
Exactly.
But it can be adapted, right?
Yes, through advanced and pretty complex usage of its internal memory spaces, the pattern space and the hold space. Commands like N let you append the next line of input into the pattern space, which allows you to load multiple lines into memory at the same time.
Enabling multi-line pattern matching.
But it requires extremely careful script writing, and honestly, this is usually where people switch to awk or Perl or Python for better readability.
Let's look at the source's complex but practical use case.
Mm-hmm.
Using sed not to edit text, but to generate commands for bulk file operations.
Oh, this is a beautiful example of the Unix philosophy. You don't write some large, clumsy program to rename files. You use ls to generate a list of file names. You pipe that list to sed, and sed uses its substitution command to transform each file name.
Like from report.new into an executable shell command.
Exactly, like mv report.new report.old.
And then you just pipe those generated commands directly into another shell.
Right. You end the pipeline with chesh. This runs a new shell, which then executes every mv command that was generated by sed. This approach is incredibly efficient and extremely flexible. The ability to use captured groups in sed to reuse parts of the original file name is what makes this strategy so powerful.
Oh, moving up the data complexity chain, we get to awk, the report and data extractor.
Awk excels where sed is weak, structured, columnar data. It was explicitly designed for writing quick reports and extracting data where the input is organized into records and fields.
And by default, it splits records on whitespace.
Right. Each line is a record, and whitespace separates the fields.
So what are the indispensable variables?
$0 refers to the entire input record, the whole line. $N gives you the total number of fields in the current record, and then $1, $2, $3, and so on give you access to the individual fields.
And awk is type-aware. It can do math.
It can easily perform arithmetic on numeric fields, which sed cannot do natively.
So if I have a log file, and I need to calculate the sum of resource usage in the 7th column, but only if the 3rd column contains the word success, awk is the clear choice.
It's tailor-made for that. You define patterns, like success, and actions, like total, plus $7, that are executed only when the pattern is matched. The sources highlight using logical criteria, like filtering lines where the number of fields and MF is exactly 7A and D, the line matches a specific pattern.
And for supreme control over data flow, we have to look at the getLine function.
GetLine takes awk from a simple line processor to a really powerful control mechanism. When you use it without arguments, getLine just reads the next input record, and it replaces the current $0 and 1 oval $2 and so on.
But the truly advanced application is reading input into a variable from an external source.
Yes. If you use command getLine var, awk executes that external command and places the output of that command into the variable var.
And crucially, this doesn't affect the current line that awk is processing.
Right. This is vital for complex scripts. For instance, you could be processing a massive user database file, and for certain records, you need to read a config setting from a separate file or check a user's status with an external command. getLine lets you manage these simultaneous input streams.
And finally, we hit the lowest level of transformation, TR character-by-character translation.
Short for translate is so often overlooked, but it's incredibly powerful because of its simplicity. Unlike sen or awk, it only deals with single characters. It doesn't understand strings or patterns or fields. It just translates or deletes characters based on 2 sets, SETI1 and SETI2.
So what are the killer applications for this tool?
First, standardizing whitespace. Often you get data with inconsistent delimiters, multiple spaces, or tabs mixed with spaces. The command trs2 will replace all consecutive spaces with a single tab character. The S option for squeeze is key there.
Which is essential data hygiene if you're going to feed that data into awk or some other parser.
Absolutely. Second, data cleanup with the delete option, DD. If you're parsing raw text and need to get rid of all the punctuation, TRD can instantly strip those unwanted characters. It's much simpler than writing a complex regex.
And the classic compatibility use case involves line endings.
Yes, converting line endings. Compatibility between older Mac, Unix, and Windows file systems always required line ending translation. Unix uses the new line character. Windows uses a carriage return and a new line. Older Macs just used a carriage return.
So you can use try to convert a Windows file to a Unix file just by deleting the carriage return.
Yep. TRD01 faith Windows file. It's basic, reliable data conversion at the character level.
We've mastered the utilities. Now for system mastery, how do we automate, schedule, and manage these powerful commands across the entire system? Let's start with scheduling processes with cron and at.
Automation is the path to true productivity gains. And cron is the system for recurring periodic tasks. Its configuration lives in the user's cron tab file, which is just a structured schedule.
The format is rigid. Walk us through those 5 time fields.
Okay, the cron tab entry requires 5 positional fields before the command. First, minute 059, second hour 023, third day of the month 131, fourth month 112, and fifth day of the week 06, where 0 is Sunday.
And you can use numbers, ranges, or asterisks.
Right. If you write 32, 1 to 5, that command runs at 2:30 a.m. every Monday through Friday.
The sources show a great example of using cron for set and forget system hygiene.
A classic is cleaning up old temporary files. An entry like 5.1 find tmp-name.back-m time plus 7 exec rm runs at 1:05 a.m. every day. It finds files ending in .back that haven't been modified in over 7 days and deletes them.
Handling critical cleanup without you ever having to think about it.
Exactly.
So in contrast to the recurring tasks of the cron, we have at for one-time scheduling.
Add is much simpler. It's used for jobs that only need to run once at some future time. You just input the job command and specify the time in a highly readable format at 17:30 tomorrow or at 3 p.m. on Friday. The system then ensures that job executes exactly once at that time.
Now, here is a piece of essential system load best practice that separates a considerate power user from, well, a reckless beginner.
This is so critical for system citizenship, especially on shared resources. If every administrator schedules their massive weekly database maintenance, their nightly backups, their huge file cleanups at a simple integral time like 1 a.m.,
They all hit at once.
those processes all hit the disk and the CPU simultaneously. This contention leads to massive spikes in load average. It can cripple the system for half an hour.
So the solution is to spread the load.
Exactly. The source advises checking the job queue with that queue and scheduling your non-critical large jobs at odd non-integral times, like 4.1 a.m. or 3.48 a.m. This deliberate randomness prevents that synchronization and contention.
These a small change with a huge payoff for system performance.
A huge payoff.
One final essential warning about the cron environment.
The environment that cron executes jobs in is intentionally minimal. It doesn't inherit your full interactive shell environment.
So it doesn't have your custom path or aliases.
It often lacks them, yes. Which is why, for reliability, every command executed by cron, or in scripts called by cron, should use absolute path names, and find, instead of just find, unless you explicitly set the environment variables you need inside the cron tab itself.
Okay, let's move on to managing processes that are already running. Job control and process monitoring.
Job control allows you to manage processes that you've stolen from your current shell session. So if you start a lengthy program in the foreground and you realize you need your terminal back, the essential move is suspending it.
With CTRLZ.
Right. This stops the process and immediately returns control back to the shell.
And once it's suspended, you can then move the job around.
You can resume it in the background with the big command, which lets it run silently and frees up your terminal, or you can bring it back to the foreground to interact with it using FG.
And the jobs command will list them all out.
Right, by a simple procession job number, like %1 and %2. And that's a key distinction. The job number is temporary and specific to your shell session, while the process ID, the PID, is the system-wide unique identifier.
So how do we get that system-wide view, which you often need when a process goes rogue or starts chewing up resources?
For that, you need the sex command. The BSD-style invocation, PISO, is the most common way to get a snapshot of all processes running on the system. It makes it really easy to spot resource hogs.
And you can couple that with uptime.
Uptime gives you a quick look at system load averages, and the command W is similar, showing who is logged in and what commands they're currently running.
And when a process needs to be stopped, how do we distinguish between a polite request and, absolute termination?
We use kill. When you run kill PID or kill % job number, you're sending a software signal. The default is sigterm, signal 15, which is polite. It asks the process to clean up its files and exit gracefully.
And most programs are designed to respect that.
They are. But sometimes a process ignores that request because it's just truly stuck.
So then you have to use the nuclear option.
In that case, you resort to kill teal, which is signal 9. This signal is non-catchable. It tells the operating system kernel, terminate this process immediately, no cleanup allowed. It's usually successful, but since the program can't clean up, it should only be used when sigterm fails.
Okay, finally, let's wrap up with some advanced exterm and GUI features, which demonstrate that even the graphical environment has deep customization roots in the Unix world.
For those who live in the original X Window System terminal, Xterm offers layers of control that a lot of modern terminal emulators obscure. One fantastic feature is dynamic customization of fonts.
And you don't have to edit config files.
No. You can access the VT Fonts menu by pressing the CTRL key and the third mouse button at the same time.
And this changes more than just aesthetics.
Right, because the CRIN window size is defined by its character width and line height. So changing the font size dynamically with this menu also forces the window itself to resize instantly. You can make it small for monitoring or large for coding.
And for workflow efficiency, we should address the limitation of standard X selection copy-paste.
X has a single buffer copy-paste mechanism. When you select text with the pointer, it's copied to one primary buffer. Any new selection just replaces the previous one.
Which is fine for simple things, but not for power users.
Right. The dedicated solution is the Splitboard client.
Okay, so what does that do?
Splitboard is an application designed to act as a historical multi-buffer clipboard. It provides an interface to store and manage multiple selections. You copy text into the clipboard selection, and Splitboard moves that selection into a persistent buffer.
So I can copy 5 different things, open the Splitboard window, and just cycle through them with next and prev.
Precisely. You gain back control. When you execute a paste, it retrieves whatever is currently displayed in the Splitboard window. This ability to capture, store, and recall multiple selections dramatically increases efficiency.
And to wrap up the networking angle, let's briefly touch on the efficiency of remote display configuration.
The ability of Unix systems to separate the execution of a program from its display is foundational. Using modern tools like Slush with X forwarding enabled, you can run a command on a remote, powerful server, say, slush remote host sturm, and that sturm application.
It runs entirely on the remote machine.
But its graphical window appears seamlessly on your local screen. All the processing and data access happen remotely, but you interact with the interface locally. It saves a massive amount of network bandwidth compared to transferring large data sets.
That separation of execution and display really is pure Unix architecture at its most flexible.
It is.
So we've covered everything, from the foundational architecture of the inode and the consequences of fork exec, through the practical application of precision, fine searches, the complex mechanics of shell quoting, function definition.
Right, and then we detailed the transformative power of the text processing, triumvirate sed, awk, and triappend, finished up with system management essentials like cron and job control.
The entire deep dive, it seems to illustrate one major truth.
Which is that the true power of these tools is their elegant composition. They allow you to chain simple, reliable commands into these vast, complex, automated workflows. But that complexity demands precision.
Which brings us to our final provocative thought for you to chew on. The Unix command line demands precision, especially with quoting. So if you run a script or a command today that uses a mix of single quotes and double quotes, do you truly know if the variable substitution or command substitution or the I/O redirection is happening exactly when and where you expect it to?
Because if you are not absolutely certain, that script is a time bomb. Understanding the fundamental difference that single quotes suppress everything, but double quotes strategically allow variable and command expansion, that is the difference between writing reliable automation and accidentally creating a huge mess.
So the homework is to go experiment.
Go experiment with echo and eval. Build a command string in a variable that includes a redirection operator and see how the shell fails to interpret it on the first pass. See how you're forced to use eval to reveal the shell's inner multi-stage workings. That mastery of interpretation, well, that's the final step to mastering the command line environment.
That's a wrap on this deep dive. We hope this knowledge helps you unlock the efficiency of the original digital power moves.